All right, so let's talk about Ohm's law and resistance. And then we'll start talking a little bit about some simple circuits. So Ohm's law and resistance. So Ohm's law, in the last section we actually introduced it, but just so we put it out there. The current in a circuit is the potential difference divided by the resistance. This is Ohm's law. Ohm's law. And it's not really a law, it's just a relationship. It's not a law of nature or anything like that. The one thing that you really need to know is that this is limited to materials that are ohmic. So limited to ohmic materials. And these are materials where the ohmic just means that the resistance is constant. Resistance is constant. Okay, so then we have non-ohmic. Some examples of non-ohmic are batteries and capacitors. So batteries and capacitors. And batteries, we know it's non-ohmic because if I rearrange this, a battery, the potential difference is the EMF, not the current times resistance. So the potential difference in a battery doesn't depend on the current flow. It's already there. It depends on a chemical reaction. And capacitors, we'll talk a little bit in the future. We'll get back to capacitors and talk about it. But that's basically it. So if it's an ohmic material, we know the resistance is constant. And if so, then we can use Ohm's law. One of the things we can look at is, say, a graph of the current in relation to the potential difference. So current in relation to potential difference. So as the potential difference is increasing, I see that the potential difference increases, the current will increase as well, and it's linear in nature, like so. And so if I break out that R out in the front, I get I is 1 over R times the potential difference. So the 1 over R is the slope of this line. So we could just find the slope and then take the inverse, and that would be my resistance. Yeah, so we'll practice using it a little bit. So what is a resistor? We'll come back to Ohm's law. We'll use it in just a second. So what is a resistor? So a resistor is anything that is in a circuit that resists the current. So it's a circuit element, we would say. Circuit element. Oops. What was that? Element that resists the current. Okay. So some examples of these, toasters. So toasters, and also if you live in an older house, those space heaters. I don't know if you've ever seen those. They glow like red hot. Space heaters. Not something that heats up in space, but rather heats up a room or something like that. And so what it does is it takes like a wire and they run it back and forth like this, except really, really tight. If you look inside your toaster, that's what it looks like. And then as the current comes in, this creates resistance, a lot of resistance. So the electrons build up and we're able to, it heats up. And so it gives off thermal energy. And that's how the toaster works. What's cool about a toaster is as the temperature goes up, the resistance goes up. So temperature goes up, resistance goes up, current goes down. So it actually, the highest current is right when you flip it on. And then as it starts getting hotter and hotter, the current decreases. And that, thankfully, because if that didn't work, like say if the resistance went down as the temperature went up, then the current would go up. So then the toaster would eventually just spiral out of control and blow out all the fuses in your house and stuff. And then we also have on circuit boards. So if you open up a computer or something, I can show you some of these in class, but you'll have these little elements like this, and they have little bands on them, and they're hooked onto the circuit board. These are resistors. And we use them because what we want to do is we want to slow down the current and control the voltage and the potential difference within a circuit board, so we don't blow out the CPU or something. So anyway, we also use them. They can use them for what are they? Like those light sensors, like if you have lights outside that come on when the sun goes down. Inside of it is a little light sensor thing. Yeah. Looks like a dollar sign. Put it over there. So there's a little light sensor inside of this thing. And so it changes with temperature. And so when the resistance, so temperature goes down, resistance goes down. So electricity can then flow through, and it turns on the light. And it's like, yay, it's nighttime. Okay, so resistors. And resistors are pretty critical for circuits, because let's go back to Ohm's law, and then I'm going to show you the FET simulation. You're going to be doing your assignment's going to be to answer some questions using the FET simulation. So let's just think of what would happen without resistance. You know what, I'm going to open a new screen real quick. Open, no. All right, so Ohm's law, the current is the potential difference divided by the resistance. So imagine if I had a circuit in which I wanted 0 resistance. What's going to happen over here? Well, you're going to break the universe because you're going to try to divide by 0. And we know that bad things happen when you divide by 0, right? So let's see what happens in a circuit. Okay, so again, I'll give you the link, but you're going to be coming out here to, I can't switch this, so unfortunately you can't see the whole screen. All right, so you got these elements over here, and on the other side you're going to have this stuff. Anyway, I'm going to make a simple circuit. So we'll just take a battery, drop it on here, and then we can start adding elements. So we'll add a wire, and then I'm going to take another wire, and I'm just going to make a little rectangle here. Boom. And the resistance in this wire, this is an ideal wire. So there's no resistance in the wire. So essentially I'm gonna complete a circuit that has 0 resistance, and we'll see what happens. Oh, it blew up the world. So what you can see is that the current goes to infinity because of no resistance. So this is called a short circuit. We've shorted out the battery. There's no resistance. So anytime you build a circuit, you need to have a resistor in there. If you don't have a resistor, things go very, very badly. So what we can do is we can just add in a resistor. So I can take this resistor. A light bulb is also a resistor, but I'll just use this one. So that's what they look like on a circuit board. Throw in another wire, and now we have a nice circuit that we can analyze. So this is what you're going to be doing for your activity. There. So you'll build this circuit, and then notice that this is showing the flow of electrons. So just to get used to it, go ahead and switch that. And here's electrons. We'll switch it to conventional flow, so you can see which way the current is flowing when we think conventionally. And then what you're going to be using is the voltmeter and the ammeter to measure the current. So if you just pull this over, you can then read the current. So we got 0.9 amps there. If I come over here, guess what it is? Oh, wow, it's the same thing everywhere. Okay. The voltmeter, so how do you read it? So the positive side, that's where you're going to read from. And then you would take this one and read it somewhere. Yeah. So you can see here, as we go across the battery, we're adding, the EMF is adding a potential difference of 9 volts. So this would be a 9-volt battery. So you'll answer some questions about that. The key here is with this wire. This is what we call ideal wire. So we'll just get that on there real quick, the definition. So ideal wire is wire in which the resistance of the wire is equal to 0. And this isn't true. We can't get 0, but it's very, 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 very small. So in effect, we can treat it as 0. But even it's very, very close to 0. But there still is some resistance. So anyway, you'll do the activity, and then we'll come back and we'll talk about analyzing circuits.